Hello, everyone. I'm Siddarth, and I'll be talking about a recent paper called LaMAR. Before I start, I would like to thank all my wonderful collaborators with whom I worked on this project. Um, yeah, so we have recently seen a lot of wonders that AI has achieved, which is you have superhuman performance with chess, Go, poker, and a bunch of these applications. But ideally, what do we want from AI? We want it to be effective with human beings. It could be like ChatGPT, or it could be Copilot, or it could be robots interacting with humans and helping us do our day-to-day tasks. So inherently, when these robots interact with humans, it's a multi-agent system because you have a human as one agent and you have these other agents like robots who are trying to collaboratively solve a task, interacting with each other and like trying to understand what each one is trying to do. So let's take an example. Um, so there's this person who wants to host a party, and it says that it has these bunch of robots with himself, and he wants to host a party, and he asks these robots to help him prepare for it. And with this instruction, these robots come up with different um, ideas, and they split this task amongst themselves, where one of them would say that I would go to the living room and start decorating it. The other one would say that I would go and get some food for the party, and then it asks for help. And based on this, and based on this request for help, that the third robot says that I would help this second robot with food. And based on all of these interactions, the human is able to decide that, okay, I have these robots taking care of all of the party stuff. I can go and invite some of my friends. Now, if you look at this problem, it's a long horizon planning problem because you have all of these robots carrying out a sequence of subtasks that involves multiple steps, where each subtask uh, could also be split into more number of smaller actions. For example, picking up a food item um, could involve does involve you moving your hand manipulator, picking up moving the joint angle at such an angle that you can pick it up and then placing it somewhere else. Similarly, navigating some position requires you to prep, proceed with a sequence of move ahead, move left kind of actions. So why is long horizon planning hard? First of all, there could be dynamic changes in the environment, there could be uncertainty, which could cause changes in the plan. And you could also forget the sequence of subtasks that are necessary to complete if you have a really long horizon of planning. Just quite similar to how human beings work. So a way to tackle this is hierarchical planning, where you have a task and you have a high level controller which takes on this task, and it splits this task into smaller subtasks. And the assumption here is that these low level tasks can be solved using traditional controllers or learn planners. Now, as we saw here, the tasks, prior work, this hierarchical planning setup had to be tailored towards the application that it was being used. But if you wanted to be used for pretty generic tasks, then you would want it to understand a wide um, area of instructions, and this is where large language models could be used. So let's take a look at language models being used for planning. So you have this instruction, it's fed to a planner language model, which generates a queue of actions that needs to be taken care of. And you feed this into a controller, you execute that action, and then you get the new observation. Now, if you look at this kind of planning with language models, um, it's quite similar to how you would create your daily schedule based on whatever you know beforehand about the meetings and the things that you want to do in the next day. So this does not really accommodate for uncertainties because each event is happening after the previous one. And it requires you to have some prior knowledge about the subtask that you would want to carry out, which might not be possible in real life scenarios. So there's another way to like mitigate this, which is reactive planning. So what happens here is you have an instruction that is fed to a natural language model. It spits out what action is supposed to be taken based on the current observation. You feed it to the controller. It executes that action. You get the new observation, and then based on this new observation, you get a new scene description, and the loop goes on until the end of the episode. Now, if you look at this reacts to the current state, but it does not really allow for long horizon planning because you are basically basing your decisions based on whatever you see right now, and there's no sense of like you keeping track of what the overall objective was. Also, in some of the prior works, this scene description was does rely on an oracle, and also the completion of like tasks. So here, what I mean by completion of tasks is if you make progress towards like completing something, um, the simulator or a human being would be giving these robots feedback on saying that you have completed this. And also the other assumption that most of like prior works take have here is that it assumes the low level controller to be successful in executing anything that you ask it for, which might not be like which does not really seem like a real like you cannot really it's not really practical enough to have it work in real world because it's inherently possible that you will run into some issues when you try to execute it. So this is where we introduce our method, which is called LaMAR, which stands for Long Horizon Planning with Language Models for Multi-Agent Robotics. So what happens here is you have an instruction and the observations, you feed it to a planner language model. The standard language model gives a sequence of subtasks, which is basically a decomposition of whatever the instruction was into smaller tasks. Now we feed the subtasks into the actual language model. The actual language model basically determines what actions each agent is supposed to take. So this is where the split of actions happens. So the assignment of which agent does which action based on which is feasible. And now once you get these actions, you execute them in the environment. So once you execute those actions, there are two things that could happen. One is the thing that the action that you took does lead to the completion of a particular subtask, which means that you need to verify it without having to rely on an oracle feedback. So this is where we have a verifier language model, which takes in this new observation and tries to see if you satisfied any of these subtasks. And what it does is it basically checks off things from this list of open subtasks that the planner language model gave at the beginning. This is quite similar to how a human being would keep track of the list of things that they want to solve for, basically checking off things from your list. So it basically updates the plan. It keeps track of things that have been completed, and it does not rely on an oracle for feedback. The other thing that could happen when you execute an action is that it might fail. The low-level control might fail. And that's where we have a character language model, which basically looks at the next step and the action that the actual language model gave as input and tries to reason about what went wrong. And based on this, it tries to suggest a corrective action. A thing to note here is that this corrective action is not executed at the same step, but is given as feedback to the planner and the actor to make better decisions off in the next steps. Overall, this loop goes on until the end of the end of the episode or the planning horizon. So along with this, we also introduced a data set called MAP-THOR, which is a set of tasks, 45 set of tasks, each instantiated with 5 different seeds. And these tasks are categorized based on the difficulty of the task, where the task could be as simple as put bread, lettuce, tomato in the fridge, where things are explicitly mentioned and like what objects you are supposed to interact with and where should you put those objects. And it could be as vague as clear the floor by placing the items at their appropriate positions, where you don't really tell what objects the language model the agents are supposed to interact with. So this categorization helps gauge the ability of language models to understand the vagueness and or ambiguity in these instructions that are given as input. Along with this, we introduce metrics and a benchmark where we compare a few other language model based methods on these tasks. So the metrics that we defined in our paper is success rate, which is basically a measure of whether the task was completed or not. So it's a 1 or a 0. You have transport rate, which gives you a judgment on a a measure on a finer sense, where like you calculate the number of subtasks that were completed. So you basically have the fraction. Uh, Ideally, you would want the transport rate to be like as close as possible to 1, which means that you completed all the subtasks that were necessary. We have coverage as well, which is a measure of fraction of like relevant objects that it was supposed to interact with. So this is measuring the language model's ability to predict what objects it needs to interact with. Then we have balance. Balance is basically determining the like trying to understand how equitable the subtasks were. So it gives a sense of like whether just one of the agents from this multi-agent team is doing all the heavy lifting and the other agents are just not staying idle. Ideally, you would want a balance closer to 1, which means that all of the agents are doing like equal number of tasks, and the number of steps, which is basically how quickly the task was completed. Along with this, we introduce an exploration algorithm, which is trying to. So, since we work in partially observable systems, uh, you don't really know what things exist in the environment beforehand, and that means that you cannot really plan before the episode, and you would need some kind of exploration. So, what happens in exploration is every agent, if it chooses to explore, it it takes in um, images in 4 different directions. We feed these images through a clip image encoder, and we get its corresponding embeddings. And similarly, we have the list of open subtasks that the planner gave as output at the current step. We feed it through the corresponding clip text encoder. We get the clip text encodings for each of these subtasks, and then we do a dot product and sum it over all the list of subtasks, and we get an exploration score based off of that. The key and we choose to move in the direction that maximizes this exploration score. The key intuition here being that you would want to explore directions that are more relevant to the list of open subtasks. So in this example, the like Alice is trying to find a laptop, and it's more probable to find a laptop on a table, which is shown in this and which is in the direction that it's facing right now, as compared to like other directions where you would not really find a laptop. So before I go into the results, here's a demo of the like Alice and Bob being tasked with putting groceries in the fridge, and you can see like Alice putting a lettuce and tomato in the fridge, and Bob putting the bread in the fridge. So here's a table of comparisons of our method with the other language model based methods. The things that I want to point out here are if we compare our method with other like architectures, we have better success rates, transport rate, coverage, balance, and steps, the number of steps required. So the key here, the key takeaway from here is that if you split the problem with tasks assigned to different modules, it helps with better planning and execution. Similarly, if you look at these two columns where you have vision and you don't really have vision, it's seen that you perform better when you have vision as input for these language models as compared to just giving text inputs. The the takeaway from here is that the corrector module, which reasons about the failures, requires vision based inputs so that it can think of like what went wrong based on the things that have happened at the current frame and the previous frame. And the other thing that I want to point out here is with exploration, you do perform better because you are able to find out missing objects as compared to having no exploration. So here's an example of failure correction where on the left side, the actor predicted pickup late, but it fails because it was really far away. So the corrector module comes up with the reasoning that says that, hey, you failed to pick it up because you were quite far away from it. So you should navigate to the plate before picking it up. Similarly, on the right-hand side, you have the actor predicting put the plate in the fridge, but it fails because the fridge is not open, and the corrective action suggested is open the fridge, and the reasoning is similarly good enough to like think about why it went wrong. Along with this, we perform experiments in a search and rescue environment where we have multiple drones working in an unknown environment. Each of these drones have a partially observable view. You have multiple missing people, which these drones are supposed to find as quickly as possible. And also, there are a few fires which spread over time. And each of these fires is of a different type, where you need water to extinguish one of them and sand to extinguish the other one. And you have water and fire sources, which water and sand resources, where the drone should go and like pick up a bucket and pour it onto the corresponding fire. So we perform experiments with increasing the number of agents, and we see here that increasing the number of agents improves the metrics, which means that these agents are able to divide up the tasks in a more efficient manner. As you can see here, like a single agent does not really do as well as having 5 agents. And that's because since the fire grows, you would ideally want to like extinguish it as quickly as possible, but you also need to like explore the environment for missing people. So the key contributions that we make here is a cognitive architecture called LaMAR, which basically divides the whole planning process into planning, acting, correcting, and self-verification, where each of these um, modules is handled through a distinct language model. It can perform long horizon planning in a multi-agent setting by creating subtasks and then assigning them to like different agents. And also we introduce MAP-THOR, a test suite and a benchmark on language-based multi-agent robotics setting, which is based on the AI to Thor simulator. Some of the limitations and future work that we think could be tried out in the future is so first of all, every query at every step we require four language model queries, which is more than the other baselines, which means that the cost of running our experiments are higher. So ideally, we would want to like move on to like smaller models, which are more specialized for like these kind of roles. So I think like using open source VLMs and like making sure that the compute requirement is lesser is something that we might want to look into the future. Also, the planning horizon that we set for our experiments was 30. I think like 30 high-level decision steps, where each decision step could involve like multiple smaller steps. So here, I think like we set it to 30 because we wanted to limit our costs incurred with GPT and like all GPT queries. But I think like if we increase the horizon limit, we could probably get better performance because in some of the experiments, the agents were really close to finishing the task, but they didn't really get enough decision steps to complete it. As we saw in the failure correction slide, the language models do have limited spatial reasoning, which means that it cannot really understand how far an object is. So injecting some form of like 3D information into the language models through some other modality is something that could be tried out. And also in the end, like performance is limited by the underlying language model. So an effort needs to be made on making more specialized modules so that they can take care of the task that they are tasked with. With that, I would like to stop and thank you guys for listening. Happy to take any questions.